Hello and welcome back to Nunley Math. Thank you so much for taking the time to join us here today as we continue our discussion of exponents and exponent rules, and we begin to transition into monomials and polynomials and look at how those are related to our exponent rules. I do want to sidestep just a little bit today to address this idea of scientific notation because it does intersect with our work on exponents quite a bit. It's something you should have studied in pre-algebra and in earlier math classes, but I do want to at least take a moment and address the fact that it does fit in here in terms of the concepts we're looking at. Now, I do have a lot of students who ask me why we take the time to study scientific notation, or why is it important, or when will we ever use it, because students tend to not encounter scientific notation a whole lot in their daily lives. So I do want to address that before we begin as well, because science has a tendency to deal with numbers that are much larger or much smaller than we tend to encounter in our daily lives. For example, we talk about the diameter of the sun being 1,390,000 kilometers. That's a large number. Hard for us to get our mind wrapped around exactly what that means. Or the mass of the sun being 15,600,000 kilograms. We don't really have much of a frame of reference for something that is that big. Or we could talk about the fact that there are 100 million sharks in the ocean. We know what a shark is. We can visualize 10 sharks or 100 sharks, but this idea of 100 million is very, very difficult for us to wrap our minds around. Or we could talk about the fact that the human body contains about 37,200,000,000 cells. That's a lot of cells, and I can think about numbers that are fairly large, but when you get to things like billions, conceptually the number's so large it's really difficult for us to have an idea of what that means. Likewise, when we talk about things that are very small, we can talk about how the diameter of the smallest atoms are about 62 picometers. Notice that's 0.000000000062 meters. And I hope I read all those zeros right. I'm reading them off the screen and I could have missed one. But it's a very, very tiny number. You know, I can think about what 1 meter is, what a tenth of a meter is. I can even think about a millimeter, which is 1,000th of a meter. But picometers or picometers are really difficult for us to get a handle on. We could talk about the fact that the mass of a carbon atom is about 0.000000000000000000000000002 grams. Of course, carbon is what makes up both coal and diamonds, so it is something we should be familiar with. It also makes up most of life, but that's a whole separate video series. But it is a very, very tiny amount of mass when we start talking about how much an atom weighs. Or we can talk about how quickly a fingernail grows. It grows at 0.000000278 millimeters per hour. But when we start dealing with numbers in this size, either this small or this large, it becomes very difficult for us to manage mathematical problems involving these numbers. For example, if I were to say to you a carbon atom is accelerating at 1,000 times that of gravity and it strikes a spaceship, does it hit with enough force to do any damage? Well, we know in science that the force of an object is its mass times its acceleration. Well, if a carbon atom has a mass of about that number we read earlier that I'm not going to reread, and we know that acceleration due to gravity is 9,807,000 millimeters per second squared, well, then we would have to calculate that out by multiplying those together. And don't forget, we had to multiply by that extra 1,000 because we're doing 1,000 times the acceleration of gravity. This creates some significant problems for us because we've got this huge number multiplied by this itty bitty number, and there's a lot of zeros in here that are occupying a lot of space, causing a lot of distraction, creating a lot of problems for us as we're trying to do our calculations. So in the scientific community, it's often considered normal to take these really big numbers and these really tiny numbers and to write them in such a way that we don't have to pay so much attention to all of these zeros. That's where scientific notation comes in. Scientific notation says, hey, let's find a way to write this using exponent rules and powers of 10 in order to make it much, much less cumbersome and confusing. So it goes something like this. Take, for example, this table. I have a 5 it has a value of 5. But if I multiply it by a 10, that 5 moves one space over, so that even though it looks the same, it no longer has the same value. It has a value that's 10 times as much because it's now located in the tens place. If I multiply by a 10 again, that 5 has moved over and has become now a 500, and a 5,000, and a 50,000, a 500,000, and a 5 million, and a 50 million. Every time I multiply by a 10, the value of this number changes, and that's represented by its location or its place value. Notice, in my original 5, the decimal point would be located here to the right of the 5. In a 50, though, now, it's further away from the 5. Further away, further away, further away. So that by the time I get to 50 million, the 5 is located over here, but the decimal is way over here. Multiplying a number by 10 causes the decimal to move one space further to the right or one space further away from that number, making the number 10 times as large. Every time you multiply by 10, the value of the number is 10 times as large. And the reverse of that is true as well. If I were to multiply by 1/10, or in effect divide by 10, notice that my 5 now becomes a 0.5. It becomes 1/10 as large. That's signified by moving that decimal from the right of the 5 to the left of the 5. When I multiply by a 10th again, the decimal moves one other place, meaning that this is no longer 5/10ths, it's now 5/100ths. 5,000s, 5 10,000s, 500,000s, 5 millions, 5 10 millions. Every time you multiply your number by 1/10, you cause that decimal point to move one space to the left, making the number 1/10 as large. Why do we care? Well, because I can take any of these numbers and I can rewrite them as 5 times a certain number of 1/10ths. I could take any of these numbers and I could rewrite them as a 5 times any number of tens. In fact, I can take any number and rewrite it so that it is a single-digit number times a bunch of tens. Let's take a look at that. Let's take our original problem. The sun has a diameter that is approximately 1,390,000 kilometers. I'm just going to bring that number down for just a second. And I want to look at where the decimal is. Right now, the decimal is all the way here at the end in red, all the way at the right. I have a large number. What I would like to do is I would like to rewrite this large number as a different number times a bunch of tens. When we talk about scientific notation always uses a number between 1 and 10, which means I'm going to take this decimal point and I'm going to move it to the left until I end up with a number that's between 1 and 10. In this case, it's going to go between the 1 and the 3, because 1.39 is between 1 and 10. But if I want it to have the same value, 1 million does not have the same value as 1. It does have the same value as 1 times some tens. The question for us is to determine how many tens does it take to turn a 1 into a 1 million, or a 1.39 into a 1,390,000. Well, we can find that very easily by finding how far that decimal had to move to go from here to here. Well, let's count that. If I move it one time, my decimal ends up being between the zeros. If I move it again, it ends up between these two zeros. If I move it again, it ends up where that comma was. If I move it again, it ends up between the 9 and the 0, between the 3 and the 9, and now between the 1 and the 3. That's a movement of 1, 2, 3, 4, 5, 6 places. It's a movement of 6 places. In fact, I would have to take my 1.39 and multiply it by 6 tens to move that decimal 6 places to make a 1 million. And this is scientific notation. Now, remember, I can multiply it by any number of tens I want, but my goal is to take this and turn it into this. It takes 10 or 6 tens to do that. Let's look at the mass, 15,600,000 kilograms. Right now, the decimal's all the way here at the end. If I want this to be in scientific notation, it has to be written as a number between 1 and 10. So I want the decimal to be between the 1 and the 5. In order for me to make these two equal to each other, 15 million is going to be the same as 1.56 times a bunch of tens. The question is how many? And that goes to how many places that decimal has to move. If I move it once, twice, 3 times, 4 times, 5 times, 6 times, if I were to move that decimal 7 times, I could turn a 1.56 into a 15.6 million, or 15,600,000. And that's your solution. Let's do one more. The human body consists of about 32,200,000,000 cells. That's a large number. Notice I still have kilograms. That, of course, is a typo that needs to be fixed. There we go. Take care of that. The important thing is where the decimal is located. Now, if I want this to be in scientific notation, I need to write it as a number between 1 and 10. So I need that decimal to be way over here between the 3 and the 7. How many places do I need to move that decimal? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. 3.72 times 10 to the 10th. That's not too bad, right? Now I can do this exact same thing with really tiny numbers as well. For example, when we talk about the diameter of the smallest atoms being 0.000000000062 meters, I can look at that and say, let's rewrite this as a number between 1 and 10. Notice, in order for that to be the case, the decimal has to be between the 6 and the 2, because I would end up with a 6.2. The question is, in order to turn a 6.2 into the number we want, it's going to have to be multiplied by 1/10. Remember, multiplying by 10 would make this number bigger. Multiplying by 1/10 would make it smaller. How many 1/10ths do I need in order for this to be in order for these two to be equivalent? Well, I need to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to need 11 1/10ths in order to make this into the same value. Now, scientific notation is defined as a number between 1 and 10 multiplied by a bunch of tens. So I can't leave this as a 1/10. I need it to be a 10, which means I need to use its reciprocal. If you remember from our exponent rules, the reciprocal is a negative exponent, or the reciprocal can be represented by a negative exponent. That's not too bad, right? Here's one. A carbon atom has a mass of about that number of grams. Once again, if I want this to be between 1 and 10, I need the decimal to be after the 2, so that it would be 2.0. The question is, how many 1/10ths does it take in order to turn a 2 into this number? Well, let's count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. It's going to take me 23 1/10ths to take this 2 and make it into a number that small. Now, because it is 1/10 and I want it to be in scientific notation, I need to make sure I use the reciprocal, so I'm going to make that into 2 times 10 to the negative 23rd. Let's do one more of these. Fingernails grow about 0.00000278 millimeters per hour. You may want to try this one on your own just to see if you've got it. I'm going to keep on going. I want the decimal to be between the 2 and the 7. How many 1/10ths does that take? 1, 2, 3, 4, 5. It takes 6 of them. And since I can't use 1/10, I have to use a 10. It's 10 to the negative 6th. Now, that is the more difficult portion of this lesson. The easier thing to do is to take things that are already written in scientific notation and convert them back to standard form. That's not nearly as bad, because all we've got to do is take the number and recognize that my decimal is between the 7 and the 8, and I want it to get bigger by 10 4 times. In other words, we're going to multiply this by 10 4 times. Every time I multiply by a 10, that decimal is going to move, making the number bigger. So 7.85 times 10 would make it into a 78.5. Multiplying by a second 10 would put that decimal after the 5, which makes it 785. Times a third 10, well, there's nothing to go around there, so I'm just going to stick in a 0. And times the fourth 10 makes it another 0. So that decimal has to go 1, 2, 3, 4 places, making this into 78500. Or properly written, that's 78,500. Let me show you that one more time. 9.3 times 10 to the 6th. I'm going to take that 9.3 and I want to make it bigger by moving the decimal 6 places. 9.3, I move it once around the 3. The second time is going to go around a 0. The third time is around a 0. The fourth time is around a 0. The fifth time is around a 0. The sixth time is around a 0, leaving your decimal here. Well, that's 930000 decimal, or, putting in my commas and writing it appropriately, 9,300,000. Last one. 1.74 times 10 to the negative 5th. Since it is 10 to the negative 5th, 10 to the negative 5th, I know I'm actually multiplying by 1/10, which means this number should be getting smaller, which means I'm going to take that 1.74 and I'm going to move the decimal in order to make it smaller. Moving it to the right makes it bigger. We're going to move it to the left 5 times. 1 around the 1, 2 around a 0, 3 around a 0, 4 around a 0, 5 around a 0, and there's your decimal point. Your number's now 0.0000174, or properly written 0.0000174. There again, a lot of teachers try and teach this by memorizing which direction to move the decimal based on whether it's positive or negative. They say if it's negative, move one way. If it's positive, move another. I find that students tend to forget that. To me, what's easier is always just to think about whether you're making things bigger or smaller. 1.74 times a 10th should make this smaller. So whatever you end up with should be smaller than 1.74. Over here, 9.3 times 10 to the 6th. This is multiplying by 10s, which means whatever I end up with should be bigger than 9.3. To me, that's easier than remembering move it right, move it left. Hopefully that's been helpful to you. Thank you so much for taking the time to watch. Make sure you like and subscribe and leave us a comment in the comment section. Also, don't forget to turn on those notifications so you'll receive all the new videos from Nunley Math. Thank you once again. Best wishes to all you guys. Take care. Bye.